is Quincy, and I'm a PhD candidate in Professor Steve Connolly's lab at UC Berkeley. My talk today is going to be about enabling high resolution and sensitivity for magnetic particle imaging with optimized receive hardware. So here's the outline of my talk. I'll introduce magnetic particle imaging, or MPI, and walk through how MPI images are formed. Then I'll talk about how new particles enable sub-millimeter resolution in small animals, mice, and how this higher resolution requires a higher receive bandwidth. So what is MPI? It's a new imaging modality that images the concentration of super paramagnetic iron oxide tracers, or SPIOs. In my lab, we've used MPI to track stem cells, white blood cells. We can image the lung, image gastrointestinal bleeds, and we've made promising strides towards imaging cancer. On the top, you can see the applications in cancer imaging, gut bleed imaging, and lung imaging. And then below, you can see a TEM image of 20 nanometer diameter SPIOs. And on the right here, you can see one of our small animal scanners that we built in our lab. So MPI has a lot of advantages over current imaging modalities. One, there's no background signal, so the image only contains tracer information, unlike other modalities like MRI or X-ray. And these iron oxide tracers are biosafe, they're not radioactive, and they get cleared through the body. MPI also provides a positive contrast, and the image is linear with the concentration of particles. So if you inject twice as many particles, your image will be twice as bright. And there is no depth attenuation. So particles that are 30 centimeters deep into the body give the same signal as particles that are 3 millimeters deep. So we don't suffer from depth attenuation similar to like optical methods or ultrasound. And these particles have quote unquote infinite half-life. So in our solid tracking experiments, we were able to image labeled cells up to 87 days in a mouse. So how do we detect a signal from these SPIO particles? So the particles align strongly with an externally applied magnetic field, and a change in their magnetic moment creates a voltage signal detectable with a pickup coil using Faraday's law. The spatial resolution depends on the magnetic transition and the gradient. So for example, a 10 millitesla transition width is roughly 1.4 millimeters spatial resolution with a 7 Tesla per meter gradient. And we typically see resolutions of 1 to 2 millimeter in a mouse. So how is an MPI image formed? We exploit the nonlinear saturation in the magnetization curve or response of the particles. In this example, we've got 3 particles in one dimension. Particle B is the only particle whose magnetization is kind of changes, while particles A and C are locked in their saturation state. So taking a look at this animation here, particle B is free to move in its magnetization while A and C are locked. So utilizing a selective field gradient to localize a particle allows us to kind of grid these signals back to a point in X space, or in our actual image. And this is the principle of magnetic particle imaging. In conventional MPI, we excite the particles sinusoidally, and the nonlinearity of the curve, as you saw before, generates harmonics relative to that fundamental frequency. So here we modulate the particles with an AC waveform, and our particle response is kind of like a saturated version of that AC waveform. And if you take the derivative of that and plot the Fourier spectrum, we get harmonics. And the detected signal actually lies within harmonics, and we reconstruct our image from there. And so a recent breakthrough in our lab with novel particles has shown an order of magnitude increase in resolution and sensitivity. So these, what we call super ferromagnetic iron oxide particles, or SFMIOs, improve resolution from 1 millimeter down to 100 microns in a mouse. So a better resolution particle is really good for a clinical translation because it relaxes the field strength requirements of a gradient, which would reduce the cost of a scanner, making a human scanner more feasible. With the example of a 7 Tesla per meter gradient field, if we can reduce that to a 0.7 Tesla per meter gradient, that also reduces the cost of the scanner by 100-fold. And so on the bottom left image is a Duranzo phantom for our normal SPIO particles and these enhanced SFMIO particles, showcasing a much sharper image quality with the new particles. SFMIOs have a much sharper, what we call a point spread function, which translates to more harmonics with more energy in the frequency domain. So to fully realize this resolution, that necessitates a higher received bandwidth. So while 1 megahertz received bandwidth might be adequate for SPIOs at a 20 kilohertz expectation, we ideally kind of want 10 megahertz or 10 times greater for these enhanced SFMIOs. So here you can see that the SFMIOs have a much sharper point spread function than the standard SPIOs. So there are 2 challenges in MPI hardware design that limit the performance. Direct feed-through from excitation limits the dynamic range, and we'd like the interference to be at or below the noise floor. And from there, we'd also like to have a low noise floor over the desired bandwidth. But current noise through an inductive coil and the coil self-resonance limits our bandwidth. So to address the first problem of direct feed-through, if we excite the particles with a transmit coil, we also simultaneously need to receive our particle signal. But during that excitation, we are also seeing the derivative of our transmit field, which couples directly into our receive coil. So we're seeing a kind of like a mix of both the particle signal VSPIO plus VFT, or our feed-through signal. And this induced voltage from the feed-through signal is orders of magnitude larger than our decided signal, which ruins our dynamic range. So ideally, we'd like this interference to be at or below the noise floor. And then if you plot the Fourier response of our particle signals, you'll see that at the fundamental, we have a huge energy content due to that feed-through. But it also contains our desired particle signal. So what we do to kind of address this is that we use a very a high-order, high-pass filter to filter out that first harmonic. And we reconstruct our particle signal, our image, using the rest of the harmonics. So the other issue that I'd like to address is the challenge of making a high bandwidth MPI. So why is that hard? Because looking at our noise model, the current noise contribution will increase at higher frequencies since we detect the particle signal with an inductive receive coil. So this limits our signal-to-noise ratio, or SNR, at higher bandwidth. And this high inductance receive coil will also resonate with the self-capacitance of the coil and the input capacitance of the preamplifier, which also limits our bandwidth. So ideally, we'd like low noise over the desired bandwidth, and we want that self-resonance to be higher than that bandwidth so that it doesn't degrade our performance. So now I'd like to talk about some strategies to address the 2 issues that I just covered. One one being able to reject the feed through, and one is lowering the noise floor over broadband of frequencies. So one way we mitigate feed through is with a gradiometer cancellation coil that's wound in anti-series with the receive coil to cancel the feed through. We need precise mechanical shimming for adequate feed through suppression. So my instrumentation includes a Vernier fine adjustment screw to accomplish this. And you can see that as we get closer and closer to a true symmetric alignment of our two cancellation coils, we were able to reduce the effective feed through by 7 orders of magnitude. So with the cancellation coil, I was able to achieve up to 70 dB rejection. On the left, you can see in the frequency domain where everything kind of just shifts down. And on the right, you can see in the time domain where the top waveform is our applied field, so just a perfect sinusoid. This middle waveform is the signal with the feed through and a particle signal. And you may not be able to see it, but there's little tiny blips on those crossover points where the particle signal actually lies. And so if you're actually able to reject that feed through, we can actually expose our nanoparticle signal right here, which kind of looks like a derivative of the Langevin curve. So we can suppress the feed through interference well below the noise floor by using some more active cancellation methods. So if we treat the feed through as a common mode interference source, we can use an instrumentation amplifier to subtract that feed through. And that would be in tandem with the gradiometric coil. So kind of a linear combination of the two, and we should be able to suppress our interference of the noise floor. So now that interference is taken care of, we can use broadband noise matching techniques to improve sensitivity over a larger bandwidth. Unlike MRI, resonant matching networks is unfeasible for MPI because we use a broad bandwidth from DC to 10 megahertz. So we rely on broadband techniques such as parallelizing amplifiers to decrease effective noise. So to achieve low noise over a desired bandwidth, we need amplifiers that have low voltage noise, but also low current noise and low input capacitance. And we need to make sure that the current noise is low and that the LC resonance is high. And then so all these efforts can achieve a sharp and bright signal. So on the left right here, we see with noise matching techniques, we get a much brighter signal comparative to the background, whereas to the right, we have a kind of relatively noisy signal. And this is a hexagonal phantom with different spots of particles at different concentrations. So in conclusion, I've shown that MPI performance is dependent on the particles that we use. SFMIOs with a much higher resolution create more harmonics in the frequency space, so you need a higher receive bandwidth to enable that. And to enable a low noise over a high bandwidth, we can employ passive and active feed-through rejection techniques and broadband noise matching techniques. All right. And I'd like to acknowledge my lab and my funding sources with a special point out to the H2H8. All right, thank you.